So far we spoke about assessment of water resources and river barrages, which means infrastructure for withdrawing water resources from rivers. By the way, during the last lecture, we spoke about a typical structure for a river barrage and said that it's something like this, with protections here. And I didn't know this is the foundation, and this is the riverbed. I didn't know the translation for this, which I call tooth. It's called the cut-off wall. There are several words for let's say that there are synonyms in English for identifying these kind of walls that are built into the ground in order to stop infiltration. And they are called in Italian diaframmi, which is literally translated also in English. In some books references I found a diaphragm wall as a translation, as a term. And I think it is more used cut-off wall. Cut-off because it cuts infiltration. And of course it's also stabilizing the foundation, meaning that it prevents the overall structure slipping downstream for the effect of the upstream pressure. So again, let's call it cut-off wall. I found also translations like clogs, but I think cut-off wall is the most appropriate. Okay, this is just an appendix of what I said during the last lecture. So, as I said, we spoke about assessment of water resources and infrastructures for withdrawing water resources. So we focused on barrages, but also we spoke about wells, and we extensively spoke about techniques for assessing how much water is available. Now we get more in detail into sustainability, which is one of the focus of our courses. In our case, sustainability of water resources use. Sustainability is a buzzword today, is a very fashionable term, because it reflects a major question mark that is now posed to modern human society, which means how much our development, our use of natural resources, our use of the land, of the earth resources in general is sustainable. Sustainability means that we need to make a use that allows us to profit at most from natural resources, but at the same time allows us to preserve the same opportunities, the same natural resources for their use by future generations. So we are concerned by overexploitation, we are concerned by producing litters, we are concerned by any human intervention that may be not sustainable in the long term. This is a challenging question mark, it's a challenging task to investigate sustainability, and the reason why it's challenging is very simple. It requires predictions of the future. Anytime that we make prediction of the future, you know that it's a challenging task. It's a challenging task that it has been always posed to humanity. You know also from our past history that humans always tried to predict the future, and with various ways. Of course, our task is to try to predict the future with objective techniques, making use of our knowledge, and this entails always uncertainty. The most let's say the most known to our everyday life kind of prediction we are used to listen to is the prediction of weather, the prediction of meteorology. And we know that this is very useful. For instance, today it's very cold. Yesterday we got a lot of rain and snow, and we were alerted 3-4 days in advance by meteorologists that this was going to happen. this is a very nice example of how much meteorological prediction is useful. By the way, the capability by humans to elaborate meteorological prediction improved a lot recently. When we talk about sustainability, we need predictions in the long term. There is a say, which is attributed, I think, to Einstein, but I'm not sure. But the say says that prediction is always difficult, especially when it refers to the future. And because, of course, when you have to assess something that is presently available, some people call it prediction, but actually it's not a prediction, but this is easy because we can observe it. When you go into the future, there is uncertainty, and the uncertainty increases with the so-called lead time of the prediction, the time horizon of the prediction. If I want to predict meteorology, this is relatively simple. If I want to predict meteorology for 2 weeks from now, this becomes more difficult. And the longer the lead time of the prediction, the higher the uncertainty. So, for what refers to sustainability, we have to predict what's happening into the future in terms of water uses and water resources availability. In terms of water resources management, which means predicting the evolution of water demands and means predicting the evolution of water resources availability. Prediction of water demands is in itself a task that is quite difficult because it entails prediction of demographics and prediction of technological development. Demographic is affected by, of course, increase of population and migration. Migration is affected by political development, and this is governed by random events. What does it mean, random? It means that there is uncertainty, which doesn't mean that we cannot predict. Randomness can be a random variable, a random process can be predicted, but there will be some uncertainty left. So we don't have to be concerned, discouraged by the fact that the process is affected by randomness. It just and only means that any assessment, prediction, is affected by uncertainty. It doesn't mean that we cannot predict it. And let me give you a very stupid example. If I toss a coin, you may say it's impossible to predict the outcome. On the other hand, if I want to see the glass half full, I could say it's very easy to predict it because it's either head or tail with a probability of 50% each. So it's very easy to predict. And it's a useful prediction because, for instance, if you make an analogy with a water resources problem, if I was able to elaborate a prediction of yes or no water for the month of August in the water supply system of Bologna with some probability, like 95% probability yes, 5% probability no, this is a very useful prediction, even if it's random, because there is uncertainty. You see, I'm not sure that it's definitely yes. There is some uncertainty, which means that the process is random. Again, you don't have to be concerned, but on the other hand, you have to be fully aware that any prediction is affected by uncertainty. And as a technician, as an engineer, you have to be fully aware of that, because, as we will see, the public generally is not aware of that. The public tends to believe that a prediction made by an engineer is that. It's given for sure. Now, I was talking about demographic. Demographic is a prediction affected by uncertainty, but it's not our task to deal with demographic. If we need a prediction of demographic expansion, we will need to seek a collaboration. with a sociologist, with a person that is expert about predictions. But if we focus on the other side is water resources availability. We can assess water resources availability today, still with some uncertainties, as you have seen. If we want to predict water resources availability into the future, we enter into prediction. Like any other prediction, is affected by uncertainty. And it's a prediction in the long term. It's not a prediction for the next week. It's a prediction for the lifetime of an infrastructure, which means 50, 100 years. This is why when you hear about predictions of climate, people try to predict it until 2100, because it's a time horizon of 8 years, which is useful for planning, for environmental planning. And therefore we enter into the domain of climate prediction. So what is weather and what is climate? There is a fundamental difference between the two. The weather is given by meteorology. It's usually expressed at the local level and for short time horizon. So we don't speak about meteorology in 2100. Meteorology refers to a precise value given at a certain location at a certain time. Precise, I mean for a given location and given time, of meteorological variables like rainfall, temperature, wind, speed. And when you talk about meteorology, you have to say rainfall in Bologna tomorrow, rainfall in Bologna from 12 to 1 today, or wind speed in Bologna averaged over 1 day, or averaged over 1 month. Never averaged along a long time horizon. It doesn't make any useful attribution if we predict rainfall in Bologna for the next year. It's not very useful. When we talk about meteorology, we talk about prediction for a well-defined time step. When we talk about climate, climate is given by simply the statistics of the weather. So we compute statistics of meteorological variables. And these statistics usually are aggregated at large spatial and temporal scales. So it doesn't make any sense to say that rainfall tomorrow in Bologna is a climatic variable. It's a meteorological variable. But average rainfall over 1 year in Bologna in 2100 is a climatic variable. It's averaged over a long time step. And I was not correct when I referred to Bologna. I would have to say over Italy, because we need to refer to large spatial scale and large temporal scale. What is the reason why, when I compute statistics, I try to refer to larger scales? Because, of course, predictability becomes difficult because I go far into the future, and in order to reduce uncertainty, I have to compute an average over big scales. If I talk, for instance, at the global level, the global average of rainfall is easier to predict with respect to rainfall in Bologna, which may be affected by local processes, local human interventions, local anthropogenic influence. If I average over larger spatial scale, I minimize uncertainty. So be aware of the difference: meteorology, short time frame, usually small spatial scales, and climate, statistics of meteorology over larger scales. When we refer to water resources availability in the long future, then we enter into the domain of climate. We have to talk about statistics. We have to try to predict the future climate, which is the large-scale conditioning of the weather, of the meteorology. To give you another example, when people try to predict the climate, they use global models. Global models because, as I said, they need to reproduce the whole atmospheric system, and therefore they cannot refer to a small domain of the atmosphere. They need to try to understand what's going on at large scales, just because they need to refer to large scales. When they need to make prediction of meteorology, what they do, they are aware of the fact that they need to reduce the scales. They refer to a small portion of the global model. They use the global model to get the boundary conditions, and then they refer to a small portion, like for instance Italy. And over Italy, they develop a more refined model that tries to reproduce not only the climate, not only the large scale, but also the weather at small scale. So the local model over Italy works at a smaller spatial scale and small time scales, because they are related. The two scales are related. Okay, so we enter, as I said, in the domain of the prediction of climate. And you know that predicting climate is a challenging task, and there is climate change that comes into play. So this is why hydrologists are concerned by, and water resources managers, by climate change. Because water resources availability is affected by rainfall, is affected by precipitation, of course, and therefore precipitation in turn is affected by climate change. Predicting a climate change is not, again, an easy task, because we need, besides studying the system in current conditions, we need to try to understand how the system, atmospheric system in this case, will evolve in future conditions. And here uncertainty again increases. By themselves, hydrologists, water resources managers wouldn't be particularly concerned by climate change, meaning that it's not their task to realize these global models, to try to predict the future climate. This is a task by atmospheric scientists, by climatologists. But of course, hydrologists need to use their input and need to make sure that this input is reliable. They need to assess uncertainty of the climatic predictions, and this is why they get interested in climate change. Not because they want to elaborate model, not because water resources managers want to predict climate, but because they need information on uncertainty of predictions. And this is why we are so concerned about climate change. Again, it's not our research field, it's not our domain, but we need to use this output. And a first issue that we notice is that this output very often is given in a form that doesn't allow a use for engineering design, because the scales may be large, because uncertainty is not specified, because sometimes we realize that these predictions outline a future situation that is difficult to deal with, because it's predicting in some cases a future situation that is much worse than today, and therefore if you want to get ready from an engineering point of view, very often we end up with a design that is not sustainable economically and also environmentally. Because if, for instance, we are told that we will have in the future 50% less water resources availability from a given source, of course what we need is to design storage facilities for a huge amount of water, huge volume of water. And these infrastructures may be not sustainable. If we want to build a very huge dam, we know that there is an environmental impact. We know that we need economic resources, which may be not available. And this is why water resources managers get concerned about these predictions that in some cases outline a very bad future, and therefore this is why hydrologists try to better understand what's going on there. So we get into discussing climate change, and this lecture, and maybe also a small piece of the next one, is dedicated to an overview of what climate science suggests for the water cycle in the future. This overview is very descriptive, and therefore it's not really something that it's a basis for tough questions at the exam. On the other hand, it's not easy to find in the literature a comprehensive picture of the effect of climate change on water resources, and therefore I decided to put together this review, which is based on essentially on data analysis, but there is also some more, that gives to you an idea, a figure of the topic. And this is important because climate change is a controversial topic. There is a controversy, a global controversy ongoing on that, which it's not really well highlighted by the media, but it's there. And why there is controversy around climate change? Of course, the explanation is very simple, because it is a very sensitive issue. It's a very sensitive issue because it's global, first of all. It's not a local problem. If we are told that there is a local problem in the United States, people in Europe tend not to be much concerned, unless it is something that can spread at the global level. So if we if we know about a nuclear explosion that may happen somewhere in the globe, and the contamination may travel up to reaching our own place, then we get concerned. If we know about a local problem that is confined to somewhere that is very remotely located with respect to our own place, we are not concerned, of course. And this is not a bad behavior. I mean, it's something that is natural. Climate change is not local, climate change is global, and therefore this is a reason of concern. Second, it's a reason of concern because for some psychological mechanism, people tend to be less concerned by natural hazards with respect to human-induced hazards. So we are not concerned at all about a possible collision with bodies traveling into the space, meteorites, I think is the right word. But we know from our past history that in the past mass extinctions may have been caused by impact with meteorites. And we know that an impact with a huge meteorite may change radically the climate on the Earth with a flip situation, with a turning point. But people are not concerned. While people are concerned by, for instance, the risk that may derive from building a dam. They are much concerned. Or people are concerned by the risk of airplanes that may collapse over cities. They are much concerned because, for some reason, natural hazards are not so, not so concerning, because probably humans tend to consider them something that always happened, something that never caused a sudden risk for humanity. And while for anthropogenic hazards, man-induced hazards, people may probably see them as something they are not used to. The moral of the story is that there is a widespread concern about climate change. The concern is also incremented by pessimistic predictions, and you listen from the TV very often that climate change may completely and radically change our conditions, environmental condition on the Earth within a few years. Some people say 3 years, some people say 5, some more cautious people say 50. But it seems like in the short future, something really bad will happen. So this is why there is this reason of concern. And therefore, when there is constant, there is a debate and there is controversy. And the controversy is about whether and where climate change is occurring. So some people question, like for instance, some people question that rainfall is increased, and also some scientists question that rainfall is increased, extreme rainfall is increased, and some people question that high flows in rivers are increased while low flows are decreased. And the controversy focuses on whether, if there is a change, it's human-induced or not. And this is the reason of concern. It's the reason of debate. It's an important debate because the solution is different. If we want to find, as engineers, an efficient solution to a problem, we have to know the problem, and in particular its causes, because if we want to act on the causes of the problem, we have to know them. So even if we accept a change in climate, our reaction should be different whether the change is given by increased CO2 emissions rather than increases solar activity. It's a different story. Especially, it makes a big difference in terms of actions for climate mitigation and action for climate adaptation. Keep in mind the difference between these two terms. So there is a fundamental difference. There is climate mitigation, climate change mitigation. So climate change mitigation, adaptation. Mitigations means that we try to contrast climate change, to limit climate change. Reducing CO2 emissions, it's a way to mitigate climate change. Adaptation means to mitigate the consequences of climate change, the impact of climate change. So with adaptation, we are not intervening on climate change. We accept it, but try to minimize the impact. I build a dam to store water. It's an adaptation strategy. Should we concentrate on mitigation rather than adaptation, or the other way around? It depends on the causes. If one is convinced that climate change is given by increased solar activity, mitigation, it's impossible. There is nothing that we can do. And therefore we focus on adaptation. If one is convinced that climate change is given by increased CO2 emissions by humans, then we can concentrate on mitigation, because by reducing CO2 emissions, we can mitigate climate change. Keep in mind that mitigation and adaptation work on different time and temporal scales. Usually mitigation works on large spatial and temporal scales. If we reduce CO2 emissions, climate is not going to change the day after. Climate change is going to slow down after maybe 30, 40 years. Atmospheric scientists say that even if we brought emissions to zero today, probably climate change will step back in 30, 40, 50 years from now. This is why they say we need to act soon. Mitigation, of course, works at large scale. We cannot reduce only the Italian CO2 emissions. We need to reduce CO2 emission at the global level. Adaptation typically works in the short time and spatial scales, because climate change causes typically local problem. It's a global process that has an effect at global level. Keep in mind that, my opinion, but it's a shared opinion, what is the main problem induced by climate change is on water resources. This is the main problem we have to focus on. Of course, there is also hot temperature, but we can find a way to remediate, to adapt to a higher temperature. Scarcity of water resources, indeed, it's the most important consequence. And scarcity of water resources, it's a local problem typically. Adaptation works at the local level, and the day after you have resolved or mitigated the impact. You build a dam, and then you work at a national level, but after finishing the dam, after the dam is filled up, the problem is mitigated. So it's a different spatial and temporal scale. Of course, you understand that ideally the two actions probably should be integrated, but again, how to integrate them depends on the causes that we need to identify for climate change. And the scientific literature is debating about it. Everything I'm saying is in this lecture, and I think now I'll scroll it down, but I need to focus on the figure above all. And I think it's a kind of unique reference, but keep in mind that unique because I think I didn't find any other review of the impact of climate change on the water cycle. But keep in mind that when we talk about climate, it's extremely controversial, so I'm sure that some people wouldn't agree with the review that I'm proposing here. Because, as I said, the topic is controversial and any review is subjective. So, we are talking about what kind of climate change? The main effect of climate change is global warming. This is something that we all recognize. And first, let me make a premise on terminology. Climate change, when we say climate change, usually, implicitly, we recognize that it's due to human influence. It's anthropogenic. And in fact, some people say anthropogenic climate change because they want to be clear. But if you don't say anything else, in the usual terminology, the usual implication is anthropogenic climate change. And this is a term that was introduced like 30, 40 years ago. A related term, climatic change, was introduced in the 70s. I think it is specified here, yeah, by the World Meteorological Organization. But this term, climatic change, indicated all forms of variability on long time scales, more than 10 years. When we talk about climate, usually this is the typical time scale we refer to, decades. This is the smaller. And but during the 70s, the term climate change replaced climatic change. So today we just speak about climate change, but again, to focus on anthropogenic drivers. As it became clear that human activities had the potential to alter the climate. And this is something that we all agree on. We admit that human activities have this potential. This is something that is agreed by scientists. So again, when we say climate change, usually we refer to the anthropogenic cause. And what is the effect of climate change? The most known is global warming. Global warming is something that, again, everybody recognizes in science. So it's unquestionable that we are experiencing a period of warming, so this is not questioned. It's important to say that very often we speak about global warming, but this warming has occurred with different intensities depending on the location. So it's not uniform. And it's important also to recognize that it happened with different intensities also in time during the season. So there are some seasons where temperature has increased more, other seasons where it's not as increased. This first picture clarifies what is the mechanism of the greenhouse effect. We don't speak about it because I'm sure that you know about greenhouse effect already. Greenhouse effect means that if you release CO2 in the atmosphere, and what happens is that CO2 builds a kind of screen that traps the heat that is released by the Earth after the Earth received the heat from the sun. And there are several greenhouse gases that can contribute to building this screen. The the term greenhouse, it's very meaningful because it's the same process that may happen in a greenhouse. You build a screen with a greenhouse that doesn't disallow the heat from sun to entering the greenhouse, but then once that the interior of the greenhouse is warmed, then of course the greenhouse is a screen that doesn't allow this heat to go out. And as I said, there are several greenhouse gases. The most prominent is CO2. There are other gases, but the most prominent is CO2 because there is a high concentration of CO2 in the atmosphere, and this is for natural reasons. And so in this way, of course, human emission can contribute to creating this screen. Of course, if you increase the temperature, we suppose that there is an increase of evaporation and therefore a change in several meteorological variables. Now, what is the magnitude of the increase? This figure, it's not good to print on the screen because it's not easy to read it. Basically, you see here the date from 1960, more or less, up to today. And you see every year a picture of the global temperature with white means no increase, and yellow and red means increase of temperature. So you see that it's not uniform, but with passing time you have the extension of yellow and red areas, which means that the temperature on Earth increases not homogeneously, but almost everywhere. Now let me, what is the magnitude of the heating? So we are talking about, on average, 1 degree, more or less 1 degree since the pre-industrial period.